All right, here we go. Properties 5.5, properties of rational functions, section 5.5. Our main objectives for the next 2 days are to find the domain of a rational function, find the vertical asymptote, find the horizontal or oblique asymptote of a rational function. What is a rational function? A rational function is when you combine two polynomials, one in the numerator, one in the denominator, and you call it a rational function. Okay? Simple enough? Yeah?
Hold up. We just got here, John.
When you combine two polynomials, one in the numerator, one in the denominator, it is now a rational function. Okay? The domain is a set of all real numbers except when your denominator equals 0. Because what can you not have in the denominator? 0. Okay? Remember, it is okay for 0 in the numerator, but it is a no-go for 0 in the denominator. Got it? All right, so we're going to find the domain. Your domain of your rational depends on your denominator, okay? So when you look right here, if I take x plus 2 and say it cannot equal 0, what would make it not equal to 0? What will make it equal to 0? So x cannot equal -2. And that's why your domain is x, such that x cannot equal -2.
Okay, hold up.
Wait, is this it?
This is the first part. Yeah.
Oh, girl.
Oh, so
Do y'all kind of remember this?
No. I remember this.
Nope. So the domain is just denominator?
The domain denominator. D in the D. Okay. All right. Good. All right. So then if you look here, example B. Notice how it's x squared minus 25. This is not factored. So before you can find the domain restriction, you have to factor if possible. So when we factor x squared minus 25, we end up with this guy. X minus 5 times x plus 5. So I'm not only setting one thing not equal to 0. Should I check? Should I go check? Make sure.
Yeah.
All right. How do we feel?
So good.
Okay. So example A is not having a factor, right? Example B is you have to factor. Yes. X squared minus 25. It's a difference of two squares. So what multiplies to give you -25 but adds to give you 0? That would be -5 and +5. Cool?
One day.
All right. Next example. Go example. All right. So here we have an example of x squared plus 1. Right? Now the deal here is if I take x squared plus 1 and set it equal to 0, I end up with x squared equals -1, and then I end up with x equals the square root of -1. And what is this? Imaginary number, right? So this means that, this is an imaginary situation. Agreed? That I got a little weird, but you see. Okay? Because of the imaginary number, what this means, sorry, the domain is all real numbers.
Wow.
So the domain is all real numbers. So if it comes down to a situation where you have an imaginary, what is the domain? All real numbers. Cool? All right. The next type that we might have is here where you have to factor the numerator, not factor the denominator, but you have to factor the numerator. Okay, so when I factor this numerator, it becomes x minus 2 times x plus 2 divided by x minus 2. Okay, what do you notice would happen to my x minus 2? They would cancel out, right? Because they cancel out, it's still a discontinuity. It still is a problem in my function. It's just that we'll learn as we go along. Instead of it being an asymptote, is what we call a hole in our function. It's a removable discontinuity, something we can just pluck out and it's gone. But because of that, our domain is still restricted. Because if I take it out of the graph, it's a part of the graph anymore? No, it's not. So my domain still has a restriction. Okay?
Wait, so why would we do all this?
Just to show you that leading into when we talk about removable discontinuities, that it doesn't create an asymptote, it creates a hole.
Okay.
All right. So graphically, what we're on table, if you look and we were to graph this, notice when I graph it as is, it's going to say error, and that's because it has that removable. However, if I graphed it without it, it wouldn't say error, right? It would work just fine. So the function as is going to create an error. The function with the removed, it's going to say it's good to go.
Wait.
This is the actual function. But if we just type it in without the removed, then it won't show you your error. It won't show you your discontinuity. So you don't want to put it in the calculator. So in the calculator, you want to put the original. So you want to put this one, not the one with it being removed. Because they're not the same thing. This is x plus 2, and then this is your rational. And they are not the same because of this little piece right here. So if you are to graph in the calculator, make sure you're graphing the rational, not the reduce. If there's a hole. All right. So let's talk about it. So here we have 1 over x squared. 1 over x squared, off the back, we know that there is an error where? What can x not equal? 0. X cannot equal 0. There's something at 0. Now, when we put this in the calculator, because it's at 0, there's no x-intercept and there's no y-intercept. So it will not cross, and it's just telling all of this. So graphically, this is what you end up with. See how it never touches, and it never touches. And this is because they're called what? Anyone remembers? Asymptotes. You have a vertical asymptote at x equals 0, and you have a horizontal asymptote at y. So that's why it has no x or y intercept. Is it going to keep getting closer and closer and closer? But nothing's going to happen. If you look at a table, you can see right here, no matter how big I put in, it's still going to keep giving me a value, right? I put in 10, 100, 1,000, 10,000, and it's still giving me a number, even though it's a bunch of zeros. So this right here is 0.00001. This is 0.0000001. Then that one's 8 of them. You get the gist. All right. So that's why we say that as it goes on, x is going to infinity, and its goal for y is it wants to approach 0, right? But will it ever approach it? No. Okay, so this is what your sketch would look like if you were doing it on paper by hand. Do you understand the asymptotes? Asymptotes again are what? Boundary lines, your imaginary boundary lines, right? All right, now, what if I have 1 divided by x plus 1 minus 2? Based on our transformation rules, these things do something. If I have a value outside of the x, what is that doing? It's a vertical shift down, right? And if I have a value within the x, that's a what? It's a horizontal shift, left to right. And our x is a liar. So even though it looks like it's going to go to the right, it's actually going to the left.
So how is that shifting?
Well, it's causing my asymptote to move, right? My vertical asymptote is affected. So this is not just a shift, but it's my vertical asymptote. And this one is my horizontal asymptote. So when there's changes in the function, transformation-wise, it's causing your asymptotes to move. So notice how I went from being here. My first shift was to go to the left 1 unit, boom. Then my second shift is to go down 2 units. So this is the new location of my function. And that's why it's important and why we keep reviewing transformation. Because without graphing, you should be able to say, okay, this shift is here, this shift is here, this is where we're at now. Okay, but in terms of rationals, those shifts are your what? Your asymptotes. All right. All right, so summary. Horizontal, vertical asymptotes, putting it together. When we're describing them, we're talking about as x is going towards negative infinity or positive infinity, what is your y value? That's your horizontal asymptote. Okay, so what's happening left to right? That's your horizontal asymptote. Okay, and then when we're talking about our y values, as x approaches some number c, some constant, and it's a boundary, that's our vertical asymptote. Yeah, so your horizontal asymptotes are going to be y. So horizontal are y equals something. Vertical asymptotes are x equals something. A good way to remember it is boy bucks.
Oh wait, I remember.
Remember Oy bucks?
Yeah.
Horizontal is y equals, and it has 0 slope. That's because it's just flat. Vertical, it has an undefined slope, and it's x equal a number. Oy bucks. It used to be my math cuss word as a child. Yeah, like when I was in class, I'd go, oh, Oy bucks.
That's kind of embarrassing.
Once I discovered it annoyed her, I did it, and now I've been punished tenfold with my students that do things to annoy me. So,
Wait, what is the stand for again?
undefined slope. But that's Oy bucks.
No, I think you enjoyed math a little bit too.
It is what it is. All right. So this is how your asymptotes can look and then their behaviors that they cause. So as you can see here, if I'm going towards infinity, I'm moving towards the asymptote. If x equals c, so I have an x value, how it can behave different and opposite behaviors. So it's just different things that your asymptotes can do. And so we'll stop here and finish tomorrow after our quiz. Cool?